Basically, you can use antimatter to study symmetries. The symmetries you're trying to look at are basically the comparison between matter and antimatter, the differences, if any, between antimatter and matter. So the two symmetries that one looks at specifically are something called CPT symmetries, where one can compare, for example, the light emitted by an antihydrogen atom with that of a hydrogen atom, or the mass of an antiproton with that of a proton. This is one area where we can study antimatter in comparison with matter. And the other area one can study antimatter, again, in comparison with matter, is the gravitational interaction of antimatter. We understand very well how matter interacts with matter, how matter falls against matter. We don't know at all how antimatter falls with matter. So the one experiment, or the one type of experiments looking at CPT symmetry, the symmetry between matter and antimatter in terms of the properties, is done in experiments like the experiments behind me, the alpha experiment, the ATRAP experiment, the previous experiment called Athena, and the Asakusa experiment that is on the floor right now. The gravitational experiment, there's only one of them, is being built up right now. It's called Aegis, and it should start studying antimatter, letting antimatter fall, in about 2013, and have an answer in 2013, 2014, if we're lucky, to see whether antimatter falls like normal matter or not. Antimatter, in principle, is absolutely innocuous if you don't have a lot of it. If you have much, much more than we could ever possibly make, then it might start getting a little bit dangerous. Right now, it's about as dangerous as a light bulb, as a 5-watt light bulb that you run for a few seconds. That's about the amount of antimatter, or energy equivalent, that we can produce at present at CERN. So antimatter in the current state and in any foreseeable future is completely innocuous. So the uses of antimatter are, on one hand, a multi-billion-dollar industry. This is called positron emission tomography. One can use antimatter to look inside the body, to study structures inside the body, cells that have a high metabolic rate, that are reproducing, that are dividing. So you can detect cancers at an early stage like that. But you can also use it to study the function of the brain, to try to see where changes in the brain correspond to changes in connecting tissue, to neurons expanding, growing, and so on. And there also antimatter helps you understand what is going on. So this is something where antimatter is already being used and has been used for the last 40, 50 years almost. Where we don't know whether antimatter may have a use or not is to treat cancer. Once you've detected it with positron emission tomography, you want to treat it. And one of the ways in which people have treated cancer in the past is to irradiate it with protons. And what we're investigating now is whether it's possible to irradiate cancers with antiprotons and possibly be a little bit more successful than with protons.